Okay, so last video we talked about the action potential and how it is non-diminishing along the length of the axon. And the notion is, how does it continue to sustain itself from the axon hillock all the way to the synaptic terminal? And this process involves what are called local currents. So here we see a type of axon that is using what is called continuous self-propagation. This type of axon is non-myelinated. And what happens is that we have the excitable portion of the membrane, and as sodium is pouring in here, right, during the upward swing, during the depolarization phase of the action potential, as sodium pours in, well, it doesn't just stay confined to this region of the excuse me, I need to be on the red, in this region of the axon. It is going to go backwards, and all those sodium ions are also going to diffuse forward as well. And so you can start to imagine that if you got a lot of sodium diffusing forward, that the resting membrane potential is supposed to be minus 70 millivolts, but as sodium begins flooding forward here, then you're going to get an upward swing, a less negative membrane potential, and eventually you'll hit threshold, and then this portion will enter into an active action potential phase. Now, why doesn't going backwards, all this sodium that's leaking backwards, why doesn't that do anything? Well, remember this yellow portion, this means that it's in the absolute refractory period and cannot engage in an action potential. So that's why action potentials can't move backwards, because the sodium cannot induce a new action potential yet. But why it self-propagates, right, requires no more stimulus, it's self-propagating, and why it is non-diminishing, because it's the same process that continues down the length of the entire axon. And you can see the movement in this series of 3 pictures. Okay, so that's why we have propagation. Now, what about myelinated axons? Well, myelinated axons use a type of propagation that isn't continuous. It's called saltatory. And you can think of it as jumping propagation. It's going to jump from node to node. And so it uses less energy. It's much faster. The rates get up to incredible speeds. We're talking about 120 meters per second. That's incredibly rapid. Think of, you're less than 2 meters, and something able to travel 120 meters per second is very impressive. So the current's going to jump from node to node, and only in these places does any depolarization occur. So nothing is happening in between the nodes to resustain the action potential movement. It does it through the length. Here are our individual cells, say a Schwann cell right here. Here is a node of Ranvier. The density of sodium voltage-gated channels and potassium voltage-gated channels is incredibly high, higher than anywhere else in the human body. And so you get a robust response that is enough, and enough sodium leakage to depolarize this entire region to cause the action potential to remain self-propagating and non-diminishing until the next node of Ranvier, where it will be resustained again. So this appears to jump from node to node to node, and we get very rapid transmission this way. So here you have the notion of a action potential in progress right here. We're getting sodium that's leaking both ways, but remember, this one's in a refractory period, cannot engage another action potential at this point. This one is ready to receive these extra sodium ions that will cause the threshold to be reached in this region, and then sodium will come in here. And so we'll see this kind of jumping from node to node to node and continue on from there. Now, as it turns out, there are also different types of nerve fibers. There are nerve fibers that we can kind of say are like hoses, right? Big, wide diameter, and can conduct action potentials very rapidly. Then there are those like the type C that are like soda straws, very thin, and action potentials are slow. Type A's are myelinated, so that helps also by increasing speed very much, and they'll engage in this saltatory conduction, whereas type C's are unmyelinated, so they're very slow. Type B's are kind of in the middle. They have light myelination, medium diameter, so forth. So the type A's are going to conduct very important information, such as when we need to move our muscles. Information from our sensory neurons is going to be conducted very rapidly to keep us aware of what's going on in the outside world. The autonomic nervous system will employ the types of B and C. For instance, type C may be the dull, aching, throbbing pain sensation that you get. And the reason it feels dull, aching, and throbbing and persist is because type C fibers are slow, but once you finally get the signal there, they persist for quite a while. So here are the different conduction speeds. Type C's get maybe up to 2 meters per second, compared to the type B's that get about 7 to 8 times faster, and then the type A's are just the super autobahns for the nervous system. Okay, so here we see that type B's, C's will go to the stomach, the viscera, the dilating pupils, those kind of responses in the autonomic nervous system that don't require incredibly rapid changes, but where you have skeletal muscles, you have to get your sensory information, you need very rapid movement and vision, right? You get visual information for humans, that's the most critical sense